Hello everyone. The topic of this talk is NoPeopleAllowed, the three-step approach to weakly supervised semantic segmentation, which won a third place at Learning from Imperfect Data Challenge. Maria Dobko and me, Ostap Vinyavsky, are computer vision researchers from the Machine Learning Lab at Ukrainian Catholic University. The outline of our presentation is as follows. First of all, we are going to describe the weakly supervised segmentation problem and its challenges. Then we'll tell you about the competition, our approach, and show the results. Finally, we'll share some ideas. The deep learning methods have proven their efficiency in semantic segmentation. They, however, require a large amount of data with pixel-level annotations, which are 25 times more expensive and 15 times more time-consuming to collect than image-level labels. We present a method for semantic segmentation which is trained with limited supervision. The used dataset was proposed by the LID challenge. It consists of approximately 460,000 images, which are primarily used for object detection tasks and is split into three sets: train, validation, and test. The images in the training set have only image-level annotations. On the other hand, validation and test, which are around 15,000 images in total, are labeled pixel-wise by the LID challenge team and are used for evaluation. The pixel-labeled data is only available for local validation. It's also forbidden to use any type of external datasets or approaches which rely on pixel-level annotations. The data suffers from high imbalance, especially towards three classes: person, bird, and dog. There are also a lot of missing labels in the data, mostly for images with class person. Moreover, we observe that class person has a large impact on other classes in the data. It usually is present in combination with others and often overlaps with such classes as microphone, sunglasses, helmet, unicycle, etc. It's thus important to have correct labels for this class. Also, we observed that the dataset consists of two parts, 2013 and 2014 subsets, out of which 2014 subset has better quality of annotations. When choosing an approach, we have studied previous works, which were developed for Pascal VOC 2012 dataset. Assessment of quantitative performance on this data showed that the top 5 methods of weakly supervised segmentation all used the self-supervised learning approach. The idea behind this type of learning is to train a fully supervised segmentation model on the pseudo-labels generated from a classifier network. Our method is based on this paradigm.
We propose an approach to weakly supervised semantic segmentation which consists of 3 consecutive steps that allow us to extract high-quality segmentation masks from image-level annotated data and train a segmentation model on them. First, we utilize the localization ability of convolutional neural nets to extract class activation maps. Then, we apply the IRNet method to rectify the CAM generated at the previous step. Finally, we train a fully supervised segmentation model followed by a test time augmentation technique during post-processing. Each of these steps we describe in detail on the next slides. Our first step is to train a classification model. To address the issue of class imbalance, we downsample each class of the dataset in correspondence to the number of samples in the least represented category. We train 2 CNNs separately, one for 199 classes excluding class person, and another one a binary classifier for person solely. And it is trained on a subset of 2014 data, which has less missing labels for this class. After the classification net is trained, we can extract the class activation maps from its last layers. You can see the results produced at the first step in the right lower corner of this slide. The tested architectures include ResNet 50 and VGG16. Even though ResNet is capable of reaching a higher classification score, it appears that the network also produces some artifacts, while VGG does not. Based on this observation, we utilize VGG16 architecture as a final model for classification step, but we also add 4 extra convolutional layers at the end of this model. Originally, to extract activation maps, one should have adjusted the model's architecture by adding a global average pooling layer before the fully connected block. To omit this step of layer modification, such techniques as GradCam, GradCam++ are utilized. They allow us to generate class activation maps without changing anything in the classifier architecture. The difference between the two lies in the normalization that was added to GridCam++. We apply GridCam to extract the class activation maps at multiple scales, which are then post-processed by dense conditional random fields. Using the models from the first step, we generated CAM for all 400,000 images in the training set. And using model confidence score, we selected around 42,000 images which have the best activation maps. We trained IRNet, a method originally developed for weakly-supervised instance segmentation to improve the quality of our class activation maps. It helps to respect the class boundaries compared to the traditional class activation maps used in the first step. So interpixel relation network, also called IRNet, estimates two types of information. First, a displacement vector field and a class boundary map. It has two branches for this, which are learned separately. The loss for IRNet includes the losses from both branches. So what is the difference between them, and why do we need to use both, or do we need to use both at all? The first branch predicts a displacement vector field. The picture on the left in row C illustrates the outcome from this branch, while D from a second branch. The displacement fields are used in instance segmentation, which is not relevant to our task. That's why we don't use the first branch. The second branch is responsible for detecting boundaries between different object classes. It is very useful for our method, so we proceed with it. Although no ground truth labels for class boundaries are given, the second branch is trained with class equivalence relations between pixels through a multiple instance learning objective. This is done to an assumption that a class boundary exists somewhere between a pair of pixels with different pseudo-class labels. When detecting class boundaries, we aim to compute the pairwise semantic affinities in such a way that two pixels separated by a strong boundary are considered as a pair with a low semantic affinity. Each pair of pixels, xi and xj, are assigned their semantic affinity A. The class equivalence between them is represented as a binary label, which is 1 if their pseudo-class labels are the same, and 0 otherwise. The affinity is then learned by minimizing cross-entropy between the binary affinity label and the predicted affinity as shown on the figure. So at this point, we have already generated pseudo-segmentation masks. On the third step, we train a fully supervised DeepLab v3+ network with ResNet 50 as an encoder. The choice of this architecture is based on its state-of-the-art performance in fully supervised semantic segmentation on such datasets as Pascal VOC. The family of DeepLab models are famous for incorporating atrus convolutionals. Employing a large value of atrus rate enlarges the model's field of view, enabling object encoding at multiple scales. The most recent model, which is DeepLab v3+, has added a simple convolutional decoder, which its predecessors were lacking. This decoder model helped to refine the segmentation results by allowing detailed object boundary recovery. So having a trained end-to-end segmentation model allows us to run inference in an elegant and effective way. So to produce the prediction of our method, we don't need to run the first two steps. Only one segmentation model is utilized. At the post-processing step, we utilize two types of test time augmentations: horizontal flipping and image scaling on 3 scales, 0.5 original scale and 2 times larger one. The combination of these CTAs result in 6 total predictions, which are averaged by mean. This step severely improves the performance as it increases the generalizability. However, each additional CTA permutation makes inference time longer. So in terms of efficiency, it is important to choose only the most impactful augmentations. Here we would like to share some of our experience that we gained while working on the problem. First of all, we observed that VGG is better for class activation map generation than such models as ResNet, which actually give us some artifacts. We also see that decreasing the output stride of VGG by removing some of the max pooling operations improves the activation maps produced at the end. Using confident and unconfident regions for IRNet is also beneficial, as it corresponds to confident background and confident foreground. The multiscale CAM gives a large improvement and is utilized as a post-processing after a few of our steps. Dense conditional random fields doesn't require any training, but it helps to rectify boundaries. This is why we use it as a post-processing after classification step. Test time augmentations after segmentation step drastically improve the result. So we use it in almost all of our experiments, and we see a great increase in the performance. Replacing stride with dilation is another technique. So we replace it in DeepLab v3+ to decrease the output stride, and then we get a better output of the models.
Since each of 200 classes is represented only by 0.5% of labels in the data, using accuracy score for measuring the performance of the classifier is meaningless. Thus, we have chosen mean F1 score as a metric to select the best classifier with. For the segmentation step, we used intersection over union metric computed for each class separately and then averaged. Besides calculating mean IOU, the LID challenge also evaluates our submission on such metrics as pixel accuracy and mean accuracy. We experimented with various thresholds for step 2, tested two encoders architectures for DeepLab v3+, ResNet 50 and ResNet 101, used TTA and added CAM for class person extracted from a binary classifier mentioned before. One of our observations is that a deeper encoder hasn't improved the overall results. We received a slightly better performance after adding activation maps for a person, however, we didn't manage to submit it on time before a challenge deadline. Our final solution is an end-to-end DeepLab v3+ model with ResNet 50 encoder and TTA post-processing. We achieved 37.34 mean IOU, gaining third place at the LID challenge. We still have some open questions in mind. Firstly, we would like to experiment with different types of regularization added on the first step to improve the classification and possibly the activation maps quality. It would be interesting to try our method on a larger subset of data, using upsampling instead of downsampling. This was omitted due to the resource limits. Also, we would like to add person class labels to the other steps of the pipeline, for example, before segmentation, as it would allow us to run end-to-end inference for all the classes and potentially could provide better results. We believe that the primary metric used in the challenge should be changed to a different one or a combination of metrics, since mean IOU doesn't account for class distribution and treats all classes equally without depending on the number of occurrences. Here is a link to slides of this presentation. Please feel free to contact us in case of any questions. Thank you for your attention.